Effects is something really complicated. Maybe I can't figure it out, or I'm not a good enough mathematician. But I can still calculate the integral if I can figure out this area. Now, I'm not going to figure it out exactly if it's all curvy like that, but I can get pretty close if I take a little piece like that, and I say, here's the width and here's the height, multiply those two together, that's the area of that piece. Right? And this is the area of the next piece, and this is the area of the next piece. And if I just calculate them, literally calculate them, take a ruler, measure it, calculate it, add it together, actually, it could be a pretty good integral. Even though I can't figure it out. I'm not smart enough to do the math, but I am smart enough to get close to the integral. That's the idea of these computational methods. All of the computational methods have the same basic idea, which is, it's always the same. I'm not smart enough to figure out the exact mathematical answer, but I am smart enough to calculate something that's very close to the right answer. So finite elements is yet another method of that. This would be an example where I take the whole thing, which is very complicated, I cut it up into small pieces. The area of the small pieces is very simple. Right? The height times the width, that's the area of the small piece. So that's easy. So the area of each piece is really easy. Add them all together, and that gives me the area of the whole thing. That's the idea of finite elements. Okay. What else under math? Numerical integration. We just talked about it, so we could do numerical integration. Now, you know that F equals MA, and A, we got that up here? F equals MA, and this A is a second derivative. So if I want to know, for instance, what is the velocity, I need to integrate the acceleration. In theory, I need to integrate the acceleration to get velocity. So if I can do numerical integration of the acceleration, I can figure out the velocity of the system. So when I say I'm doing numerical integration, I'm not doing it just because I want to do the integral. I'm doing it because I want to solve some other problem, like maybe a motion problem. Okay? If I did numerical integration twice, I could get the position. Right? Acceleration is the second derivative of the position. The first derivative of position is velocity. The second is acceleration. So I wrote numerical integration, but it could go the other way. Differentiation. What do we use radar for? What do we use radar for? When we have a radar system, like say at the airport, what are we using the radar for? So we're measuring the flight of the airplane, right? We want to know the velocity. Where's it going? So that we can keep airplanes from running into each other, for instance. Okay, so usually when we use radar, we're trying to figure out the velocity. In the United States, it's very famous. Police use radar on the side of the highway to tell if you're driving too fast. If you're driving too fast, they have a radar, they aim at your car. And if it measures your speed too high, you have to pay a fine. It makes you mad. It's expensive. So we use radar to measure velocity. But what does radar really measure? How does radar work? Some people would say that radar won the Second World War. That Germany, when it began the Second World War, was unstoppable. Right? In the early battles of the Second World War, Germany just won everything. And then they tried to invade Britain using airplanes. And Britain had developed radar. Because Britain had radar, they could tell where the German airplanes were going, and they could always intercept them. And the Germans could never figure out how do they do this. No matter how tricky they tried to do, the Germans always knew where the British always knew where the German airplane was going to be, and they could go and fly and intercept it. Save the war. Using radar to measure velocity. But how does radar work? What is it? There's a broadcaster on the ground, and it sends out some kind of a signal. What kind of signal is it? It's a wave. It's a radio wave. That's where the RAD part comes from. If it goes out, it hits something that reflects radio, usually metal. It hits a piece of metal, and then it reflects some of the radio back. And there's a receiver right beside the transmitter. It transmits back, comes back, and you can measure something. What do you measure? You measure how long it took for that bounce, right? So I send out a signal. It's a radio like most signals. It's cyclical. Looks like a sinusoid. It hits a piece of metal, and then it comes back, and I receive it. And I can tell how long it took by counting the number of cycles. Okay? So now I know how far away something is. So what does radar measure? Position, right? It only tells me how far away it is. It bounces off, it comes back. So how can I tell what the velocity is? I'm not measuring the velocity. Radar measures only position. Yeah, that's the numerical differentiation. That's the idea. So let's see how that works. You've got it. The change in position with respect to time, right? That's supposed to be velocity. So this is x at, say, t plus delta t minus x at t. That's the change in the value of x divided by the change in the value of time. Only this isn't equal, right? This is equal if we have a limit as delta t goes to 0. Then it's the derivative. But on a real radar, there's a time. You can't measure with delta t equal to 0. It takes a little bit of time to make each measure. Okay? So it's only approximate, but it's good enough to get a good enough measurement of velocity that you have a good idea where the airplane is going. You can go and intercept it. I can also tell if I'm in the control tower in Hanoi and there's a couple of planes coming in to land at the airport. I can tell from radar if they're going to be so close together that it's dangerous. Then I tell one of them to turn away or slow down or something like that. Make sure they're not too close to each other. Okay? So let me talk about this for a minute because this is one area that I happen to have a lot of expertise in. So why wouldn't this work very well? Like for instance, suppose I can build a radar where delta t gets smaller and smaller and smaller. When I look at this equation, I want the limit to get the real velocity. I want the limit as delta t goes to 0. So if I can make delta t get smaller and smaller and smaller, that's good, right? It's not good, it turns out. It's not always good. Why not? What's wrong with this? First, let me ask you this question. In this equation, if I'm going to calculate a numerical derivative, where do I get the number that I put in right here? What number is that? What does that come from? This is a position measurement at this time, t plus delta t. So here's my radar. I make a measure. Here's the thing I'm trying to measure. I make a measurement at time t. Right? This distance is x. That's the thing I'm trying to measure. So if I measure time t, that number goes right there. Then a little bit later, whatever delta t is, I do it again. And maybe in the meantime, this thing moved over here a little bit. So now when I measure x, it's going to be a little bit bigger number. That's this number. Then I calculate the change in those two numbers, the difference, right, the minus sign, and I divide by the delta t, and that tells me approximately what the velocity is. It's beautiful. It's beautiful. It saved England. It saved England from Nazi Germany. The English think it's beautiful. Maybe the Germans aren't so happy. It's a beautiful idea. Okay, so what goes wrong? How could this possibly go wrong? Do you think there's such a thing as a perfect measurement? No, I don't think so either, right? So there's no perfect measurement. So let's say we have, every time we make a measurement, there's a possibility that there might be a little bit of error. Now I'm going to change this equation a little bit to account for the fact that maybe there's a little bit of error. Let's see what that equation looks like. It would look like x at t plus delta t plus a little bit of error, let's call it e, at t plus delta t, minus x at t plus a little bit of error at t. Divided by delta t. So now I'm going to split this up. Everybody agree with this equation? See how I did this? Right? This, theoretically, this is perfect. This is perfect. I make a measurement at one time, put that measurement here. I make a measurement a little bit later, delta t later, put that measurement here, divide by delta t, and that should be approximately the velocity. But I know that when I make the measurement, it might not be perfect. So now I'm only writing the equation with the error in there. So here's where the thing really is, but there could be a little bit of an error. And this is where it really is, but there could be a little bit of an error. Right? Divided by delta t. So this is equal to x at t plus delta t minus x at t divided by delta t. So far, so good. But now there's this other part. The error at t plus delta t minus error at t divided by delta t. That's just straight algebra, right? That's nothing fancy about that mathematics. So this is the part that's extra now. This is what the error does to me. Okay? Everybody agree? So now that I know that there's a possibility of some error, this is what the error would look like inside of my calculation. So now what's the problem if my radar is really fast? If I can take measurements really fast, according to this, to get the best velocity, I want the limit as delta t goes to 0. But look at this. What happens if delta t is really small? It turns into a multiplier, right? Let's suppose delta t is 1/10 of a second. Suppose I can make 10 measurements per second. So delta t is 0.1. If I divide by 0.1, that's the same as multiplying by 10, right? If I have some error, I multiply by 10. So I go out and buy a better radar. You know what the problem must be? I need a better radar. Now it's 1/100. It gets 100 measurements per second. That's got to be right. 100 has to be better. What happens in this equation? It multiplies the error by 100. Damn. I need an even better radar. I'm going to get one that does 500 per second. That's got to be good. 0.002, 500 per second. What happens over here? It multiplies by 500. The error is just getting bigger and bigger. So what's the right answer? How do you fix that? How do we fix this? What's the technology? How are we going to do it? This is the beautiful thing I talked about earlier. It's not easy. Nobody's figured out everything yet. That's why you can get a job when you graduate, make a lot of money. But first, you have to be an expert at something. Okay, I happen to be an expert at this. I can explain lots more, but it's not easy. It would take me a long time to explain how we fix this. But there are some ways that we can fix this.
So you fix it?
Yeah, I did fix it. Well, there's a few things you can do. One thing you can do is you can take an average velocity by looking at more than 2 changes. So suppose this is the function. What we did was take a point here. In essence, what this equation does is it takes 2 points and it calculates the change this way, right? That's the numerator. And the change this way, that's the denominator. That's what this calculation is. It's calculating the change this way divided by the change that way. The true derivative is when you shrink this down to 0, what does that ratio turn into? That's what the derivative is. That's math. That's pure math. But numerical, real world, you can't make that interval 0. It has to be some finite number. So it's a finite number here and a finite number here, and that's what they are. Now, to try to make it smoother, to try to get rid of some of the error, what I could do is take this one and do it over again. And then maybe take this one and do it over again. Maybe back up one, do this one. And when I go to estimate the velocity at each point, instead of using only 2 points, I could use 3 points or 4 points. Make a weighted averaging point. And count the most recent one counts more, but the others also count. They all need to stay on the line. Because, for instance, in this region right here, the velocity is always positive, right? The real velocity is always up. But over here, if I have a random error that's getting added in, so let's say I measured this thing and it's a mile away, it's a kilometer away, but in one measurement I measured 1001, and in the next measurement I measured 999. So the error would be 1001, the error is plus 1, 999, the error is minus 1, 1 minus 1 is 2 in the numerator, plus 2. So I calculate an error that's too big, it's positive. So this is the real slope that's going up. But in that case, the error would make it look like it's even steeper. But I could do a lot worse than that. I could have the 999 here, 1001 here. Now I calculate a negative slope. Right? That's completely wrong. It's one thing if the slope is positive and I don't get the number quite right, that's not so bad. But if the slope is positive and I calculate a negative number, that's bad. Right? If it's really an airplane, and let's say what I'm trying to measure is how fast is it coming down. Here's the runway. I want the airplane to land. If the airplane is really coming down, but I make this calculation, and what I calculate says the airplane's going up, then I tell the pilot, you need to go down faster. Okay, that's potentially a disaster. Maybe he's already coming down just right, but I tell him, I calculated your velocity, you're going up, you're not going down. Oh, okay, go down faster. It's not good. It's not good for business if you kill all your customers. It's not good. So how could I avoid making that sign error, the SIGN, plus versus minus? Well, one way I could do it is if I calculate several in a row and take the average. The average is going to stay positive or negative, even if one of them gets wrong. So even though if it's coming down and I calculate 10 in a row, maybe one of those, by mistake, because of the error, one of those gets calculated positive. But the other 9 will overcome that. Will say, no, you're going down. It's okay. You just made a minor mistake on that calculation. So that's one solution, is to spread out the number of measurements. Don't do only 2 measurements. Use 3, 4, 5, 6. However, if you do that, the problem with doing that is that by spreading it out over a lot of measurements, you slow down the possibility that it could change quickly. So if the real function has a fast change, you'll miss it because you're taking an average. You'll calculate something that keeps going up until a little bit later because you're taking an average. So when it first starts back down, it won't change the average to the other side. It'll stay positive. We can talk a lot more about this another time. I think this is getting long-winded. So, okay. Anybody have any questions today? What I hope we talked. I believe that what I'm presenting. Let's back up a minute and talk about the whole course from day 1 to right this second. I believe that what I'm presenting is coherent and makes some sense. Okay? I think it does, but maybe it doesn't. So you have to tell me if it doesn't make any sense. So here's what I think we've done so far. At the very beginning, we talked about what exactly is even engineering. What is that? Then we talked about what is an engineer, a personal engineer. We talked about how in history it wasn't anything. It was whatever anybody said it was. But today it often has a legal meaning. The legal meaning in the US and a lot of other countries is based on accreditation. You're supposed to have found out what the legal meaning is in Vietnam. Is it based on accreditation? What is it? We talked about how once you become an engineer, you can join the Society of Engineers, and that's how you can maintain a professional contact with other engineers. It should be like an exclusive club, right? If you finish 4 years or 5 years and become a mechanical engineer, that should put you in a position that's different from anybody that didn't do that. Hopefully you know something that other people don't know as a mechanical engineer. And you want to have as your friends, at least some of your friends, should also be mechanical engineers. Your colleagues should be mechanical engineers. You can communicate with them through organizations like Professional Society. And I talked about ASME because that's the one I know best, but there are others. There are other mechanical engineering societies around the world. Right? Maybe one in Vietnam. Did anybody look? Okay, well anyway. So now today what we talked about was within mechanical engineering is a very, very broad title. Inside mechanical engineering are lots of specialties. There are big categories of specialties. There are 4 main ones, but under each one of those 4, there's also a lot more smaller categories and smaller and smaller. The higher you go in your education, the more of an expert you become. Usually the narrower the category gets smaller and smaller. To be really an expert at something, you have to get into a very narrow category. And why is that? It's because for the last couple hundred years, millions of smart people have tried to do exactly what we're all doing, trying to become knowledgeable about mechanical engineering, and a lot of them were really smart. And so when they decided, I'm going to work on CAD, or I'm going to work on HVAC, or I'm going to work on vibrations, or I'm going to work on nano composites, those smart people keep pushing the state-of-the-art farther and farther out, right? More and more advanced, so that for you to catch up with them, you have to get very narrowly focused. So I think it's important for you to imagine which piece of mechanical engineering you might be most interested in so that you can focus on it. But not yet, because you're still taking all of the first level courses. So we had 4 categories up here. You had a class you didn't have a class yet out of the solids category. You had 1 class out of the fluids category. You just finished 1 class out of the motion category. And you're about to take 1 class out of the math category. That's this computer class. Okay, so it's starting to fill in. But for the next 2 years or 3 years, you'll keep taking more classes out of each category. So you don't have to pick yet which one you really want to be special in. But I think it's always a good idea for you to imagine. Right? So when the time comes, you'll be ready to make a decision. Okay, does that make sense?
Yes.
The course makes sense?
Yeah.
Okay, I propose that we take tomorrow off. And I have one more thing I want to propose. Those of you who came before, you just finished the other course, and you should do the presentation, so relax. And we'll start the computer class Monday. Now, I want to do one more thing. I want you to take a very short quiz right now. Yeah, very short quiz. Yeah. So everybody take a piece of paper. Is everybody ready? You should have just a clean piece of paper, no notes, no talking, no looking. Okay. underneath each one, we put some subcategories.
So we list four main categories and under four main we list more.
Say that again, please.
We list the four main categories and then under each.
You don't have to put anything underneath, just the four main categories. Yes, based on today. So, I'll give you a couple of hints. There was one over here, and it started with an S. There was one here that started with F. There's one here that started with D. There was one over here that started with M. Those are the four. I want those four things. Just write those four things. You should be writing your own, don't look at your neighbor. This can't be that hard, they were up here all day.
So for a specialty and topics, do we have to add more?
You don't have to do any of those special. No, just the four categories is all I want, just the words. I only want this.